Well, they're not. Maybe they'll pick up shortly. We want to pick up where we left off last time. I did send you some more material. After we leave this chapter, we will not cover everything in each of the chapters. We'll cover selected materials. Today, what I'm going to cover is I'm going to finish up the discussion of the quality solution principle, where it comes from, and I'm going to move to lasers. Let me document to them.
I guess nobody here got invited to the lunch.
I'll be honest. All right, let's go back to where we were when we left last time. Okay. So when we left last time, we were talking about if you had an atom, for instance, that had two indistinguishable electrons. But indistinguishable particles can be beyond electrons inside an atom. They can be two atoms that are so close together they're indistinguishable. So you can think of there's classical particles inside the gas molecules up here in the air, and all the gas molecules can be thought to be the same. So if you didn't color code them or label them or something, you wouldn't know the difference. But in the case of the gas molecules, they're far apart. And because they're far apart from a classical sense, they actually have a location and they have another location. In the case of electrons and quantum particles, they don't have a trajectory in the classical sense. All right? They have a probability over an area. So although I've drawn them kind of like they're specific things, they're really a wave function. They're not at a specific point. All right? So if those wave functions overlap, then you can't tell if you found an electron that comes in a particular place, which electron in fact it is. They're indistinguishable. All right? And we talked about the fact that the first electron would have some kinetic energy, and it would have potential energy, and it would have a Hamiltonian. So the total wave function is going to depend on both electrons and where they're at. So this psi here isn't the psi of just the first electron. It's of the whole atom. And so that psi depends on all the coordinates of the first one and all the coordinates of the second electron. And if there were 10 electrons, then there would be 10 positions, if you would, of the electron if you want to identify where they're at. So it has all of those. And of course, it also would have time if we were looking at the time-dependent part. So if you applied this Hamiltonian, what you would get would be the energy of this red electron, let's say. On the other hand, if you look at the kinetic energy and the potential, this is for the second electron, so that's the Hamiltonian of the second electron. If you applied the wave function, you should get the energy associated with that second electron. Now, there's two electrons, so it makes sense that what there really is both of these guys can act on the wave function if you want to find the total energy. In other words, if you want to find the total energy of the thing, what would you do? You find the energy of the first electron, you find the energy of the second electron, and what would you do to get the total?
Add them together.
Add them together. So just like you'd add E1 and E2, you would add all of these things up. So the total Hamiltonian is the sum of the kinetics and the sum of the potential. So what most people do at this point in your book does, although he uses little h's instead of my big, is he said, I want to write all of this down. I don't want to write this every time. I want to write all of that down as simply h, the Hamiltonian, and we'll put a 1 to indicate it that it's all of the stuff related to the first electron. So the kinetic energy depends on the motion. That is how the coordinates of the first electron are changing. It depends on the distance here, which is that distance there to that electron. And the second one, it's Hamiltonian, and it only depends on the second set of coordinates. And because those things are true, and as long as we neglect the fact they talk to each other, and they would, because two charges would interact. If you neglect those as small effects, then all of these terms only have either a 1 or 2 in them. So they never differ by more than 1 coordinate anywhere along, so you can separate the wave function. And furthermore, all the 2's are by themselves and all the 1's are by themselves. So you can write the wave function here as the product of 2. The product of what is the first electron's wave function times the product of the second wave function. Now what your book has done is the following. He said, That's what we're used to. Having these coordinates, which are probably r, theta, and phi. But if this is a 2s electron, that's where the first electron is, he's in the 2s state, there's no reason to believe that the second electron also has to be in the 2s state. It might be in the 1s state or the 2p. So he's chose to use these A and B's to represent different states. Right? We good so far? We understand what the notation the book is attempting to do. The coordinates have the ones. They represent the particle, which particle you're talking about. And the A's and B's represent the state. That would be the quantum numbers. He just didn't decide to write N1, L1, M1, S1, all that junk. Okay, he just wrote A and B. Now here's the question. If they're truly indistinguishable, if I was to take the brown electron up here and swap him with the red electron where your eyes were closed, would that change the probability of finding the electrons of this atom in some particular place? No. And that's a condition that's not built into any of this math yet. So there's additional conditions that one has to consider, like the fact that you don't know which electron is which. So whether or not you had, this is R1, meaning first electron, or this was R2, meaning it was the second electron, and you put the first electron over here, you should not be able to tell the distance in anything you can measure. Key point, anything you can measure. All right? Well, let's say we measured energy. Well, if we measured energy, then we would apply the total Hamiltonian. Well, what would happen is that when you applied H1, it would change the energy you get. You wouldn't get EA, you'd get EB, because if you switch the R1s and R2s, then the first one would now be in the B state. So that's not all the energy. H2 would now give you the energy for the A state. So the total would be EA plus EB, which is just the same thing you got before. So switch the coordinates, didn't change anything measurable. What about probability? Because probability is something we can measure, like the location of the electron. Well, the wave function isn't what you measure in probability. What you measure is an operator applied to the wave function, like I just did with the Hamiltonian. Or you measure the square of the wave function for probability. So it doesn't say that the wave function has to be the same. It says the probability has to be the same, which is the square. So let's look at that. So I know that's kind of a bore at it, but just if it helps you a little bit, so be it. They really don't go around orbits, we know that. But here, I got the black and the red, so this equation state here would be this state. So I'm going to call the black being 1 and this being 2, and so there's the black, so he's 1 and he's 2. So if I had a state like this is state A and this is state B, if you would. They don't have to be in different orbits, they could have different angular momentums. I just chose to make them so that they're pictorial, okay? And so over here, this is A and this is B. So for this case, this particular function would be psi A of the first, because that's the black one that's in it, and then in the B state is the second. And the energy would be whatever's EA plus EB. And over here, when you look at this one, you have a different wave function, because this time side B has R1 in it, and side A has R2 in it. First particle's in the B state, second particle, the red one's in the A state. Have the same energy. These are degenerate states. can't tell the difference by taking out the tongue. They have the same energy. They're indistinguishable. Give us the same sort of information back. Okay? How do you get from this to this? You just flip the coordinates. Now, what I want to look at, since the particles are indistinguishable, you must have that if you take the square of the probability of that, which means take that function and multiply by its complex conjugate. That's the probability distribution. You have that. That has to be the same thing as this one when you take its complex conjugate. It doesn't say that if you exchange the coordinates that it has to equal the wave function. But it says when you take the wave function and you square it, it's multiplied by its conjugate, you got to get the same answer. Now see, 1 is not equal to minus 1, but 1 squared is equal to minus 1 squared. So there are two possible solutions to this. When you flip the coordinates, it could be equal to itself, but it also could be equal to the negative of itself. Because when you square a minus 1, you'll still get a plus 1. And the only thing we know is the square. We don't know. The wave function itself is never a measurable thing. We measure the square of the wave function, probability. We never measure the wave function. So you can't say anything about something you can't measure. You can't say it has properties because there's no way to verify those properties. So we have two possibilities. Two possibilities. And only two possibilities. The first one is when you switch the coordinates, that is, you switch the particles, the wave function is unchanged. So if you switch those two particles around, you take R2 and you take R1 and flip them, it doesn't change. It's equal to the original wave function. This is known as the symmetric solution. And particles that obey that are called bosons. These are the integer spin particles that do this. Now, something else I did intentionally, the book didn't do, but I did it intentionally. I didn't write this the same way I wrote it down here, because I want to emphasize something. Switching the particles moves them to different circles on my little graph, conceptually, if you want to think about it. Moves them to different states. Switching the order that you write a product doesn't change anything. Okay, in other words, whether you write the wave function for the A state first times the B state, or the B state first times the A state, that doesn't change anything. That's not moving particles between orbits. All right, so you're allowed to flip these, but moving these coordinates inside the circles actually picks electrons up and moves them in the orbits. That's a very different thing. All right, so flipping them mathematically, the function doesn't do anything, but moving these guys is like picking these particles up and switching places on them. That changes stuff. So if you do that, that's what we're talking about. The fact that you multiply the functions e to the ix times e to the ib is still e to the ib times e to the ix. That's just regular multiplication. Switching which one of these things you put into the television set, that makes a difference. If you don't know that, there's a big difference if you put the TV set in the bathtub and the water duck, the little rubber duck on the table, or you put the TV on the table and the rubber ducky in the bathtub. All right, very big difference. So switching what you put in, which is what these things are, they're the inputs, has a huge impact. I know they don't give Jaden rubber duckies yet. He's got to grow up a little bit more for the years. He's got the small toys from McDonald's. All right.
Little ducks.
The other possibility is the following. You switch the question. This time what you get is this. You get a minus sign in the wave function. So if you think about it, this is even and odd, right? But we're not talking about just flipping x to minus x. That's what we talked about there. This, instead of flipping the coordinate axis around, what you're talking about is exchanging the particles. So it's a very similar type of idea. And when you square that, and you square this, that minus sign will go away, and you get the same condition. These guys are called fermions.
The first one was called the symmetric solutions.
This is the anti-symmetric solution, as you might guess. Although usually they don't talk about it here, they talk about it when I finish the next step. Now, you can't tell the difference between those two. So the most general solution is some sort of linear combination of these two guys. And the most general solution of this is some linear combination of those two. So if you really want to write a generalized wave function that'll represent anything, then what you have is the following. This psi could be written something like 1 over the square root of 2 times psi A, R1, psi B, R2, plus psi A, R2, psi B, R1. There you have all possibilities both equally treated. Okay? So that would be the boson's wave function. I'm going to come back to that because I want to look, I'll put boson here. Because what we're going to want to do is we're going to say, what if this happened, B happened to be the same as A? Would anything bad happen in this situation? Okay? And likewise, we can do the same thing for the fermion. That'd be 1 over the square root of 2. You can leave off the square root of 2 if you want. We're going to have to normalize, obviously. Then you're going to have a psi A of R1, psi B of R2, minus psi A of R2, psi B of R1. Where I've accounted for the fact that this guy happens to have the opposite sign to represent the same thing. And here's the interesting thing. What happens, okay, for a fermion if you make the two electrons in the same state, so A and B are the same? So what his interest is to look at this one. He says, what happens? Well, he doesn't, but he says it in words. In which case, the wave function psi A is the same as psi B. Really, that'd be a better way of saying that. So those are the same state. So they're both 1s and they're both 1p. They have all the same quantum numbers. They have the exact same mathematical function. Well, it's just algebra. You just plug it in and look, see what happens. So if that was what would happen, I'd have this. The fermion would have some coefficient, let's leave the square root of 2, since that's what I chose. Then I would subtract psi A of R2, psi A of R1. Now, what did I say about switching the order of the functions themselves and how they're multiplied? Does that matter? Mm-hmm. So you could just flip those if you like. So what is this equal to?
0.
That's 0. All right, now what's the probability when you square that of finding an electron in that state? 0. So it never happens, and that's the reason for the Pauli exclusion principle. If the thing had the same wave function, there'd be no probability of ever finding it. So it cannot have the same exact state. Because if it does, then the wave function is 0, and the square of that is 0, and there's no probability of ever finding it anywhere in space. That does not happen with the boson. If you make these the same, they add together and just makes more of them. It's not a problem. It has to be normalized appropriately, but it's not a problem. So the anti-symmetrical one kills itself. So fermions cannot exist with the same quantum number. There are other ways to write this. There are matrix methods to write these. In the matrix methods, what happens is you have this matrices and 2 rows of them are the same. So when you look for the determinant, it goes away. Because they're not independent equations anymore. Right? Either way, the bottom line is there is no wave function because these 2 terms knock each other out. So you can't have 2 electrons, you can't have 2 protons in the same state, you can't have 2 neutrons in the state, you can't have any 2 type of fermions in the same state. It never happens. If it could happen, nature would like the lowest energy, every electron to be in the 1s state. But that's not what happens. And you'd have very different chemistry. You basically, everything would be down like a 1s, and it could be some sort of like super hydrogen for everything. Gases. Does not happen. Now, bosons, like photons, they like to be together. They like all being down the lowest energy state. They just love, they're clingy, they're social people. Fermions are like physics people, they're not social. Right? But they're what make the world go round. They're the matter that makes things important. Right? But they're not ones who tend to cling around and hang around. So even in the real world, there's these social ones and there's these unsocial ones that hang around here.
I'm pretty social.
Of course, what's really important is the interaction between the social and the unsocial ones. Energy versus matter and how that interacts is everything in the world. All right.
Jaden.
Now, what you can do with that is you can explain basically the periodic table. So if you start, you got n equal 1, you got L equals 0, you got ML equals 0, and you have 2 possible MS's. You have +1/2 and -1/2. So that means that there are 2 states. N, L equals 0, ML equals 0, and spin of +1/2, that's one state. N equal 1, L equals 0, ML equals 0, MS equal -1/2, that's the second state. You can put 2 electrons in it. So one electron goes in, another electron goes in, and that's it. Notice what happens to magnetic effects. As you start putting these guys in, when you have one of them unpaired, you have a magnetic moment. So it has some magnetism. When you put the next one in, it's in the opposite direction. It cancels it out. So you end up with a noble gas that has no magnetic moment. Then you can go up to the next one. You have the same sort of things for the S state, and then of course you get these P states. Well, they have 3 different guys over here. You have ML equal -1, ML equals 0, ML equal 1, and you can put 2 in each one of those states. So the next thing that happens is it becomes somewhat magnetic, tends to lose it, gets more, gets more, gets less, gets less, gets less. So in the middle of the periodic table, as you start going on, you begin to get more magnetic things. Now, there's not a lot of orbital angular momentum, so you don't get really big magnetic moments yet. When I get to the next one, I start getting over to D, I get more of these guys in a line, so I get more magnetism, and that's why iron and nickel and such are highly magnetic. Now, funny thing is, as you go further up, it doesn't do that. Why? You remember, these things are really not at the same energy. They're split. What eventually happens is some of the S lines get lower than the D lines, and so you begin to get people to say, instead of filling up like this, I'll hop to the next level. And it begins to get cancellations again. But everything about the periodic table, everything, can be explained from this chart. The way chemists usually do is they'll do things like this. They fill, called an Auerbach filling chart, where they go and they fill this, then they fill that, there's nothing here, then they'll go along and they'll fill this, and then they'll start filling down along the line. It gets more complicated in the lines with fluxing, but everything's explained if you can do quantum mechanics. You may need a computer, but it's all done. In fact, people who do really high-level chemistry use computers, and they have to take a similar type. Art Lowe is teaching quantum wave functions right now to physical chemists people. So everything is explained by the Schrödinger chart. There are other more advanced courses in atomic and such, and if you want to know more about those sort of subjects, you can. The last thing I want to talk about this is, let's take the case where we had a bunch of electrons for an atom, and let's talk about what happens when you don't get to have one atom by itself anymore. In particular, let's talk about what happens when you start mixing gases, liquids, and solids, and you have a lot of atoms, and the atoms start getting close together. When they get close together, their electrons, wave functions, begin to overlap. In other words, they begin to interact, which we left out because we didn't say they could interact in any way. What the heck is that going to do to everything? Well, if you had a single set of levels, let's say you had a level like this, this,
Can you move the paper down a little bit?
Okay, oh, thank you. Appreciate that. So you had n equal 1, maybe n equal 2, and n equal 3, and so forth. So you had a nice set of levels, right? Well, that would be atom 1. And all of his electrons would fill up the correspondingly. And over here would be another atom. And it would have the exact same levels with exactly the same set of energy levels and quantum numbers as this atom did. And as long as they're far apart and they don't interact much, their wave functions are independent and they're unchanged. And so if you were to look at a spectra of this thing, you would just get transitions that exactly match what you expect for a single atom. But what would happen if you bring those atoms start together? Well, what happens is these two atoms' electrons start interacting. They can't be in the same wave function because now they're together. There's a combined wave function for the whole atom, not for each individually. And we know that if you have a combined wave function, these electrons can't be in the same states because it's like a molecule. If they were in the same state, they're fermions. They cancel. So what has to happen is these wave places has to change. In other words, to describe it, you don't just need the three or four coordinate quantum numbers for this. You need 4 quantum numbers for this and 4 quantum numbers for that. But they're the same quantum numbers. Well, they can't be. So what has to happen? These guys interact with forces, and they disturb these energy levels, and they shift them a little bit. So the number of levels should stay the same. But what will happen is you'll have splitting. You have 2 levels like close to here. Down here, maybe you'll have 2 like this. I didn't put enough levels, okay? So these are my S's, there's my P's, there's my D's. So the original values were probably like right here in the middle. So you'll have some levels that are lower, You'll have some levels that are slightly higher than you would if the atoms are by themselves. You'll have the same total number of electrons that you can put in there because you've got all these electrons to put in, but they will not go at exactly the energy they would before because the electrons are talking to each other. Now, these are very small shifts. And these are very big shifts, so it's easy to tell which ones are which. What if I put in more atoms? All who originally had the same guy. Well, then I'll need to get more shifts. I need to get more splitting. What if I put 10 to the 26th atoms close together? Oh, we're going to get a whole bunch of freaking splitting. Well, in fact, you can get so much splitting that these guys run together. Or you can get so much splitting if they don't run together that this thing, right now looks discrete. But I eventually can get them like this. They're still discrete, but they're so close together that the energy of the room is enough to make them move anywhere in there. When you do that, they call that a band. And this is where band theory for solids and electrical engineering comes from. It's by the Pauli exclusion principle of putting a bunch of atoms together. So, in your textbook, and I'm sorry you have to deal with my drawing, but my original system where you could just add atoms to the computer and watch it build the levels no longer works under the new Windows. It's only old Windows DOS compatible software. And I doubt they're going to stop everything to write us a new quantum program just for our own benefit. It was like $30. Where's the bands? Better picture is. So here's just a couple of atoms put together. So there was the original, but they're very far apart. There's only one energy level for each atom. And then they get closer and closer together. And as they get closer together, they begin to overlap and interact and talk. When they interact and talk, one of them gets driven down, one gets split up. If you keep pushing them closer and closer, then the interaction can get bigger and bigger. Now you notice there seems to be some minimum energy level here. Well, what that usually does is that's what's going to determine how far the atoms want to naturally stay apart. This is what determines things like bond lengths in chemistry and such. If you put more, you can see you get a whole lot more bands. And eventually, if you put enough, for all intents and purposes, it's just a solid highway. So if you're up here in the conduction band, because, oh yes, there's a lot of metals and they're all close together, then you basically can have any energy in here and it takes nothing to move along from one atom to another. That's where bands come from. And it's possible that this splitting is so large that it overlaps or crosses another band. When you do that, you get a very specific type of conductor that we'll come back and talk about. All right, that finishes all the discussion of the Pauli exclusion principle. My intention is to leave that material now and to move to lasers. Lasers. Stands for light amplification. By stimulated emission of radiation. In fact, there are things that have similar properties we discussed called masers. They were found first, and that stands for microwave amplification by stimulated emission of radiation. All right? So, lasers are when you're generally talking about optical systems, but this holds for things beyond that. So it's an acronym. It's like at NASA. It's a 5-letter word, all right? But it's incredibly powerful because of the properties that it has. Now, lasers, in many ways, the processes and the rules by which classical lasers work were solved by Albert Einstein, and he solved them almost 40 years before a laser was ever invented or built. So what is a laser? Well, to understand a laser, obviously we want to know about amplification. How do you amplify the amount of light? You get more light, it appears, at least a useful type of light. You should be careful about that. You cannot violate conservation of energy. You're converting something into the right type of light that you want. Right? By a process called stimulated emission. So you have to understand what the heck stimulated emission is. And to understand stimulated emission, you got to understand regular emission. So it's time to go back and talk a little bit about why atoms emit radiation and absorb radiation, and what are the probabilities that that occur, and how does this thing, which is very important, totally differ from the regular type of emission. It has very unique properties, properties that make it far better than like a table. A table can't be made into a laser. It doesn't have the right properties, but it emits and absorbs radiation. That's why it can be warm. That's why you can see colors. That's why when you burn it, it can give off a glow. But it cannot be made a laser. So what exactly is stimulated emission? So 3 types of emission. 2 that are important as both a trigger and as a loss mechanism, and the real one that I want to stimulate. So let's start with spontaneous absorption. Well, it's exactly what you would think it is. It's the absorption of a photon by a system. It could be absorbed by an atom. It could be absorbed by a molecule. It could be absorbed by lots of different things. It could be absorbed in terms of different ways. But bottom line is, photon comes in, photon goes away, and the system is in a higher energy state. So if you drew a picture of it, it looks something like this. I'm only going to draw 2 states. There probably whole millions of states. But there it is. Let's say we're going to deal with the electron. There's the electron. Photon comes in like this. This state's energy is E1. This energy is E2. Now, that photon has to have a particular frequency if it's going to be absorbed and move this to here. Because we're talking about photon goes away. This guy went up to the higher energy state. So what is the requirement for this guy to be absorbed by that guy and go to that higher state?
The same energy as the change in energy.
Bingo. So the energy of this photon has to match the difference in these 2 energies. That's the Einstein requirement. So this is E2 minus E1. So if he doesn't have the right energy, it won't occur. So it's energy specific. Now he could have other energies up here, and maybe he could go to a higher state, drop down, or whatever. But what we're talking about, you match the energy levels, and this guy goes up. That's called spontaneous absorption. And it happens like that. Now, what's required for it to happen? Well, if there were no electrons down here, it wouldn't happen at all, right? So it does depend on there being electrons down here. So we want to talk about the thing happening here. There's some probability we'll call that B12. I don't know what that number is for the moment, but I'm just going to say it's whatever value, maybe it's 20%. Probably not good with that.
B12?
Some number. Huh?
Oh, B12, like the vitamin?
Yeah, but I'm going to have, but the reason I chose it was I used from 1 to 2.
Oh, okay.
Guess what happens when it goes the other way, I'm going to call it?
2 to 1?
2 to 1. That's the book's choice. And it turns out they're going to be equal to the same value, so they're just going to eventually be called the beat coefficients.
Okay.
It also, if I want to know the number of electrons that can do this, however, it depends on some other things. If there are no photons come in, this is like a batting average, okay? If there are no photons, there are no pitches thrown to the batter, how many hits will he get?
None.
None. So the number of these guys that can do this depend upon there being photons. So if we start looking at the number of transitions, then we need to realize this is, of course, going to depend on B1 too, the batting average, but it's also going to depend on the number of photons. Well, this is our energy density, the field density. In other words, remember that this guy, in terms of the black body radiator and such, this guy can have lots of different energy photons. And the only ones that count are the photons at that frequency that match this. All the other photons don't count. So you can throw all sorts of other baseballs over his head to second base, wherever, but only the ones going to the batter count. So it depends on this function. If you forgot that, go back and look at black body radiators when we derived that thing. So this is the number of photons per second that come across right here. And of course, it depends on there being batters. If there are no batters and you throw to the catcher, it wouldn't help either. So we'll call the number of batters N, and it's in state 1, so we'll call it N1. So the probability of getting this transition, or the number of transitions, depends upon how many photons come in. Double the photons, you'll double the transitions. Number of atoms that are in the bottom state, double the number of atoms, you'll double the thing. Have no atoms to make the transition, none will happen. And the number of these photons that you have. If you raise the temperature of an object, you can change the number of photons. Or you could shine a light, or you could do lots of other ways to change photons. Next possible method. The next one is called spontaneous emission. I should have put spontaneous. Oh. Probably not this time, but next time get why that's important. So this occurs when you have the following. You have two states again. But this time the electron is sitting up here. And then a little while later, he says, I'm not in the lowest energy state. And I want to be in the lowest energy state. So he goes down to here. And he emits a photon. Where's my grade here? And that photon's energy is going to be equal to the difference in energy of the system as well. So you get the photon back. So you can shine light in and the light would come back. And this is what we've been doing all along. So what would be? Well, if that's all there was in light, there wouldn't be any lasers. Because I haven't done any stimulated emission. I've only done, you heat the light. Now it might make sense. What do you think about the probability of this thing? Just inherent batting average from going here versus going down there. What do you think about those two batting averages?
They suck.
Yeah, you think they'd be the same. They may suck, they may be true, or may not. But you'd probably be the same. So if they don't like to emit, they also don't like to absorb. And you can prove that in what it does, and I will. But the fact is, it almost makes total sense. It should be probably the same. Because they have the same wave functions, they have the same shift. Why wouldn't it want to do exactly? It's the same energy going in, it's the same energy coming down. Well, if you do that, and you pencil this guy in, we can call the probability here, we'll call it, because we don't necessarily, you can sit there and try to figure these things out, but I'm going to call, let's see, what do I want to call this one here?
B21, right?
I'm going to make sure I use the right coefficients for this. I don't want to call him 2-1. I think your book chooses to call him A. Make sure that I haven't mixed my symbols up in my notes. Okay. And I'm going to call him A. I want to call that probability A. And I'm not going to put a 1 or 2. And the reason I'm not going to put a 1 or 2 for this is that I've got two processes by which I'm trying to talk, but this one is going to kind of be a separate process, and I'm not going to connect him with the B. So anyway, Einstein chose that. The number of transitions. Well, it's going to depend on A. That's 1. Notice that no photon comes in. The B's are all connected to problems in which a photon comes in. There's no photon in this, so there's no U this time. Doesn't care if there are any photons exist. But it does depend on the number of guys up here, so it depends on M2. So that's the number of transitions. Depends on whatever this probability is between the two states, and depends on this N2. And this N2 depends on their... Now, what do you know about the number of electrons probably in the second state compared to the first state if this was a normal thermal equilibrium, you just heated it?
More.
There are more in the hydrogen
Oh, wait,
state?
no, sorry, low.
There'd be low. So it's more likely, there is always some atoms that could come from a high state down and emit a photon. But it's more likely there are more atoms in the low state that would absorb. So if you heat or shine a light on something, then what should happen is that it absorbs that. All right? And that will raise more up until you reach some sort of equilibrium where they're emitting about the same. So you do not expect there to be more photons emitted than photons to come in. Where are we at on time now?
42.
All right, still got a little bit of time. So let's deal with the last of the three weird terms. So those are normal, those haven't changed anything. Here's the one that's weird. Stimulated emissions. In this case, what happens is, you're back up here, and you have an electron right there, E2 minus E1. And a photon comes in. And that photon happens to match the energy difference between these two. And it tickles that electron. And that electron is so enamored with this beautiful photon that it decides to fall down and emit its own photon. Electron goes down like this. Wow. But if you get a clone, you don't just get a photon. You get a photon that's in phase, in the direction, with the same energy as the first photon. I mean, it thinks that she's so pretty, man, it'll do anything. It matches completely up with it. Okay? And it goes wiggling off. Now, that means that these guys actually constructively interfere. If I build a device to kind of like a cavity, I can actually make them all go in the same direction in a point, and I can send them to the moon, and all the way to the moon, you know, 500 million miles, the things will not deviate by more than maybe a millimeter or two. I can get intense beams out of this thing. Yeah.
What material is the photon?
Well, it has to have a particular type of state. What it has to have one of these energy states where I can get more electrons up here than are down here, because my problem is this. As this guy comes in, if it finds anyone like this, then it's going to get absorbed. Now, sometimes it will stimulate, sometimes it will absorb. But if there are more electrons in the bottom, which we said there should be, it's more likely it gets absorbed and less likely that it gets. I have to find a material that I can get more electrons in the high energy state than the bottom. I can't do that just by heat. I got to do some sort of tricky little quantum physics stuff to make that work. I mean, it's not as hard as getting a date for Giovanni, but it's not a trivial type problem. So for this one, the probability, and that's where we'll end for today, is B21, and the number of transitions is equal to B21, and yes, depends on there being photons, and N2. Now here's the thing, if this laser is going to run at steady state, the number going up has to eventually equal the number going down. There are two ways to go down. You add up this and this, put it equal to the other, and solve that equation for those coefficients. And this is a universal statement of energy, so you could use for your U the black body formula. And that will enable you to solve these coefficients.
So
I did that.
we would use the same stuff we used from chapter or the earlier test?
Yes,
Vines?
you still need all that stuff.
Or Wien's formula, whatever that is?
Bean's formula. No,
Yeah.
I'm thinking more difficult than that. I was thinking all that probability distribution stuff.
Oh, crap.
Oh, yeah. Well, you think I covered that? I just thought it was randomly useful junk to stick up there? Of course. I needed it later on. Otherwise, I would have ejected that part from the book.
I just thought I could use that to impress chicks.
Oh, well, you're going to need something more than that for impress the shit. All right, I'll see you guys. Read that section of the book. See y'all later.
Does the transition have to be
If you're going to match these conditions, there could be lots of different ones, but if it's not here, then you're not going to get that energy. And if that doesn't match the photon, you're not going to put it in the This photon has to stimulate a transition between two levels that match. Yes, it's good, but every higher energy is less likely.
This is where it works.